Hi, welcome back to AP Physics 1, Unit 7. So again, last unit of the curriculum, okay? You have two videos left. You have angular momentum and conservation of angular momentum. So again, we've talked about linear to rotational equivalence. Well, you can see it right there. This is the angular equivalent of momentum, okay? So angular momentum is the rotational analog to linear momentum. So if linear momentum is inertia and motion, then angular momentum is moment of inertia and motion. Okay? So angular momentum is directly proportional to two quantities. One is the moment of inertia. And the other is the angular speed. Right? What are the linear to rotational equivalents, right? If it's P equals mv, that's our momentum. Okay? Well, the formula just becomes L, which is our angular momentum, equals I omega. M is I, V is omega. Okay? So that's just your basic equation, right? I times omega. So the moment of inertia times omega. So remember, we have all those moments of inertia that you can plug in there. Okay, so you got the 1/2 mr squared, mr squared. You have, so I do want to show you a little bit of a derivation for another version of this equation. So if I have a person running towards this merry-go-round, right, and they're going to jump onto the merry-go-round and sit at a distance r, right, from that center. Okay, so that person we can treat as just a point mass or a point object out at that distance. So what we can say is they would have an I of mr squared. Okay, now linearly, right, because this would be a linear motion, well, that's V equals R omega, but I need to solve this for omega, so it'd be V divided by R, okay? And so you would now derive a second equation for angular momentum, especially if it is an object traveling linearly towards a rotating object, okay? This R, one of those R's cancels the one on the bottom, and you end up with just mvr. So a second equation for angular momentum, especially if an object is moving towards a rotating object, is mvr. Okay, so when you push a merry-go-round a spin a bike wheel, a lazy Susan, which we'll see in our example problem, you're going to exert a torque, right? So if the torque is greater than the opposing torques, the rotational speed will increase, the angular momentum thus increases. The greater the torque, the quicker the increase in angular momentum. This is what we call the rotational equivalent of that impulse momentum theorem. So if I exert a torque for a time period, I'm going to change my angular momentum, right? Which means I'm going to change, I will have I delta omega, okay? So this right here is the rotational equivalent of impulse momentum theorem. Okay, so let's look at an example problem. I mentioned it before. We talked about the lazy Susan, which is that cool thing that probably sits on, your grandparents' kitchen table, right? And spins. It's got like the salt, the pepper, and all that. All right. Oh, so actually, that's going to be our second example problem. I apologize. So this here is, what is the angular momentum of Earth? Great question. Okay, assume the Earth to be a solid sphere rotating about its axis. The mass of Earth, you can see it's almost 6 times 10 to the 4th kilograms, a radius of 6.376 times 10 to the 6 meters, and it rotates on its axis every 24 hours, right? So the first thing we need is omega, right? So it's going to travel 2 pi radians in 24 hours, right? It's 1, let me go take a step back, right? Race big, right? So it's going to do 1 revolution in 24 hours, right? But that would give us revolutions per hour. We want radians per second. So I'm going to do our conversion, right? So 1 revolution is 2 pi rads, right? 1 hour is 3,600 seconds. 60 minutes, 60 seconds gives us 3,600. And so our angular velocity or angular speed of Earth is going to be 7.27 times 10 to the negative 5th radians per second. We also need to calculate our I value, right? Our moment of inertia for Earth. Well, I said solid sphere. And so the moment of inertia for a solid sphere is 2/5 mr squared. And that's going to be 2/5 times 5.979 times 10 to the 24th times 6.376 times 10 to the 6th squared. And I didn't calculate this number on my problem. Did I do that? No, on my sheet. So I'm going to pull out my calculator. So exit. So I have 0.4 times 5.979 exponent 24 times 6.376 exponent 6 squared. So I have a value of 9.72 times 10 to the 37th, and it's going to be kilograms times meters squared. That's the unit for a moment of inertia. Okay, now I can do my I omega. Okay, and so I have that number, 9.72 times 10 to the 37th, times my omega, 7.27 times 10 to the negative 5th. And now I can do my calculation. So answer times 7.27 exponent negative 5. And I get a moment of inertia, or excuse me, angular momentum of 7.07 times 10 to the 33. Now you have to be careful of the unit. It's going to be kilograms times meters squared per second. Okay. The way you look at units, radians, when you have other SI units mixed in, it's just going to be a unit of 1. All right. Now let's look at the lazy Susan question. Right. And so we have this lazy Susan spinning around. We're going to exert a torque on it. We're going to find the angular momentum, the final angular momentum, if it starts from rest, the final angular velocity of it, and then assuming that the inertia is going to be a disk. Okay. So here we're going to start with our change in angular momentum is going to be tau delta t. Well, but tau, remember, is r times f, right? Delta t. But if my initial angular momentum is 0 or starts from rest, I can just simply say that L equals RF delta t. And so it's has a radius of 0.260. Okay, it has we apply a force of 2.50 on it, 2.50 newtons, and then we do that for 0.150 seconds. And so our final angular momentum is going to be 0.0975 kilograms times meters squared per second. Okay, now since we know that this is our L value, we can just simply now plug in L equals I omega, and we're going to solve it for omega. So it's going to just be L over I, but we do need to calculate the I value, right, because they tell us a disk, so a disk is 1/2 mr squared. So I can just simply say L over 1/2 mr squared, right, or I can do a little bit, be 2L over mr squared, right. If it's a fraction in the denominator, I can inverse it there. So 2 times 0.0975 divided by our mass, which is 4 kilograms, times our radius, which is that 0.260, square that. And so my final angular velocity or angular speed of our lazy Susan after applying that force is 0.722 radians per second, right? So here's the answer to B. And then here's our answer to A. So angular momentum 0.0975, and then angular speed of 0.722. Okay, so again, we talked about three conserved quantities in mechanics. They were energy, momentum, and now we're going to dive into the third one, which is angular momentum.